Hey guys, this is the first video that I want you to kind of look at, and then we're going to look at some other videos, then come back to this. But last time we talked about wind formation, and we've talked about kind of this picture here a little bit too. So what I want to look at is where the wind is going to be flowing on the map here, and then we'll add something else to it. And then we'll come back and add some more to the drawing. So this is kind of just the first thing, just to kind of go off of what we did last time. And what we need to look at is what we need to look at is the direct sunlight here. So remember we talked about the sun's rays are most direct here. And if you didn't quite catch why that's the case, when you get up to these higher latitudes or lower latitudes, it's the same effect either way. The sun's rays, when they come in, will hit the atmosphere, and because there's a curvature here, they will deflect some, right? So when you're coming straight on, it doesn't deflect, so it goes straight in. So that basically it's kind of like the surface of a shield, right? So if you looked right here, as if we were to throw something at this, it would hit and bounce off. Here it would hit and come straight back, but it would be a more direct hit. Since the sun is shooting sunlight, light, basically will bounce, but not like a rock bouncing off a shield. So it basically is going to go right through and be absorbed a little bit more within the atmosphere and then by objects on the surface. So if we've got that, then let me get that out of the way real quick. Then what we really need to look at is where on the planet, and I think we've covered this several times, so I'm not going to spend too much time, but where on the planet it would be hottest, right? And we should know that as we get close to the equator, it's hotter, and then obviously near the poles, it's colder. So now if we apply what we learned about convection cells to this, if air is coming up from the equator, so it's warming over the equator and then rising. So if we were to kind of look at the surface here, if air were rising at the equator like this, right, then that means that air would be coming into this area that it just left, right? Which means that air would be then completing the circle, right? It would start to cool down here and then sink here, right? So it would basically look like that. If I can, let me fix that arrow right there. So it would basically do that right there, right? So if that's what's going on, then basically everywhere along the equator, and it's kind of hard to see this in 2 dimension, but everywhere along the equator, air would be rushing into the equator at the surface, right? Same thing would be going on. Same thing would be going on down here, right? Same idea. Okay. And then at the equator, air would be rising here, would be going over here, sinking there, right? So you basically have the same thing going on both sides of the equator. So air is moving straight toward the equator at the surface. So these would be surface winds here. And those would be moving toward equator. Right? So this way up here would be our upper level winds. And those would be moving away from the equator. So we'll just say away from equator. Right? If we've got that, then we're in pretty good shape to start developing this a little bit more. But before we do that, this is kind of like the whole laminar versus turbulent thing. This is the crayon drawing of what we would expect to see, but this is not what we will actually see, so it doesn't actually look like this. Now, we will still have surface winds moving towards the equator, so be sure you know that, and we'll have upper level winds moving away from the equator, but it's not going to be that easy little picture. And the reason for that is because we have this little phenomenon that has to do with the rotation of the Earth. So I'm going to pause this here and then come back and talk to you a little bit on big screen about the Earth's rotation, and then we'll watch a couple other videos, then come back to this drawing and fix it and finish it. So pause, unpause, and we're back. So what we're going to talk about is the rotation of the Earth. So I've got my good old trusty styrofoam globe back out, and notice that I have New York and Denton still marked on that dude. And then I have the sun over here, right? You can't see it, it's out of the screen, but I have a lamp that I'm using as the sun, and that dude's out of screen. And then I can probably help the situation make it a little darker. That's real quick, yeah. So we got this dude, and now what I want to look at is the rotation of the Earth. So I'm gonna take this dude off its stand for just a minute, and then I want you to notice that New York gets the sunlight first, right? So we need New York to get the sunlight first. So if New York gets the sunlight first, then that means we have to rotate this way, and then you can't see it because it's on the back side, but New York is getting the sun first, which New York should get the dark first. There it goes into the dark. Denton's getting dark. So dark, dark. So this is the right way. So we wouldn't go this way, because if we went this way, Denton would get the sun first. We want New York City to get the sun first. So the Earth is spinning like this, right? Now, if we view it from the pole, I haven't changed anything, I'm just viewing it from the pole, right? So let's see if I can get this up here. So notice New York is this peg, sorry, it's backwards here, and then the second peg here is Denton. So notice that New York gets the sun first, Denton gets it second. So if we were to describe from the pole which way we're moving, clockwise or counterclockwise, in this case it is moving counterclockwise. A clock would be going this way. It's hard to do because I'm mirrored on the screen. It would be going this way. Counterclockwise is this way. We are going counterclockwise, right? Now, just to show you I'm not doing any funny business, this is the way we're going, right? I'm now going to look from the southern hemisphere. So I'm not changing anything, I'm still spinning the same direction. And notice, use South America there as kind of a guiding light. Notice that South America now is going clockwise. Right, so it'll be this way. And just to show you that I'm not fooling with you. Right, that's the same thing. So, northern hemisphere is going counterclockwise. Oops, sorry, wrong way. Counterclockwise. Southern hemisphere is going clockwise. It's going to be really, really important. I'm going to show you a couple other videos on here about that. That rotation causes a little dude that's, I'll just go ahead and ruin it for you, it's called the Coriolis effect. Now, the Coriolis effect basically says that when you're moving across the surface of a rotating body, so the surface of the Earth is rotating, right? When you're moving across the surface of a rotating body, there is an apparent deflection. So from our perspective, things look like they curve. They're really going straight, but they look like they curve. So I'm gonna leave it at that and then let you kind of see some videos that flesh that out. and then we'll come back and finish up the drawing. So watch the videos and the links, and then hopefully that'll give you an idea of Coriolis effect, and then we'll talk about what that does to winds at the surface and aloft, and then we will go from there.
Amazing catching skills, right?
Hey guys, so this is a video that I wanted you to watch. I'm gonna kind of talk through it with you. I'm gonna let it play. You're kind of running through a merry-go-round scenario here of they're playing catch. If you don't know what a merry-go-round is, it's a big fat metal disc that's in a playground that you spin really fast, and then centrifugal forces and whatnot are all at play, and people go flying off. We actually used to play a game when I was a kid, because we had them on just about every playground, really big ones, much bigger than this thing here, and we would play a game called merry-go-round dodgeball. It's pretty sweet. Anyway, basically what would happen, or the premise of it, was that someone would stand at the middle with a ball, and as the thing spins around, you would basically kind of sidestep with it because you're in the middle, so you could just kind of pivot, and then you would throw the ball at someone, right? And excuse me, oddly enough, the funny thing that would happen is the person you're throwing at really didn't need to worry. It was someone either 2 or 3 down from the right or left that needed to worry. So this kind of illustrates that, and it illustrates the Coriolis effect, which, I mean, I've already told you what we're looking at, but it is the Coriolis effect, which is not an actual force. Basically, it's basically whenever things are moving across a rotating surface. So in this case, it's going to be the rotating surface is the merry-go-round. For us, what we're looking at is wind on the surface of the Earth. The Earth is rotating. And we said, remember that the northern hemisphere is rotating counterclockwise, the southern hemisphere is clockwise. So when we get this thing going, it's going to be going counterclockwise. So this would be what happens in the northern hemisphere. But as something moves across a rotating surface, as it's going, it goes straight, but to the observer on the surface, it appears to turn. And so because everything's on the surface of the Earth, when fluids try to travel in a straight path, so wind or water try to move in a straight path, they actually will curve due to the deflection of the Coriolis effect. So this kind of demonstrates that. So we'll kind of walk through it. The first thing he says here, just so we can kind of make it go faster, is this girl here is going to throw the ball, and then he goes around and asks what they think's going to happen. The girl says that if you're going fast enough, she thinks that it might actually come back to her, which is actually right. If you were going fast enough, which he doesn't get the merry-go-round going fast enough. This dude across from her says that he'll catch it, that he's that good. He's really confident. This guy says that he thinks the ball will go to the left of this dude. So he doesn't think that it'll go straight, but you'll find out he actually has the wrong idea. And then this guy basically says that this dude doesn't know what he's talking about, that he's way too overconfident, and that this guy here, is actually going to catch the ball. So imagine if they're rotating in that circular or that counterclockwise path. When she throws the ball here, he's going to slide out of the frame of reference, and he is going to slide in to the frame of reference. So really, this dude is actually right, and we can see that here in just a minute. So we're going to let it get to the point where they're about to spin this thing and roll it and throw it. So let's see what happens. He's interviewing them here, and here he goes. He'll hit play. So notice they're going counterclockwise. So notice he did catch it. Now the cool thing is, when we view this from above, And notice that this camera is actually, let me stop for a minute. The camera is moving with the rotating surface. So the camera itself is actually experiencing this deflection as well. So it's going to look like it's deflecting. I'm going to show you another video here in just a minute that shows you a little bit different vantage points. One fixed to the rotating surface and then one that's not fixed, and you'll be able to see that straight line versus the curved line. So if it's on the rotating surface, you'll see the curvature of that. So let's watch it. So you see how the ball looked like it did this loop right here. So the ball went away from her and then curved to the right. So let's see. Then this view is kind of fun too. This dude's ready for the ball. She's about to throw it to him. But it's going to, this is the point of view of the ball, so the ball is going to curve to the right. So let's watch. Oh, let me rewind that. That jumped a little bit on us. There we go. Kind of cool, right? Okay, so I have to narrate here. Basically, she's saying that the ball would go to the right. I don't know why this video is not working, but she said it just appears to go to the right. And then he's talking about how it seems that the ball, is moving to the right. It's bending, but really that ball's going straight. And then he asks kind of why that's happening. And then he calls it the Coriolis effect, which is basically where if you have a rotating surface and you throw something, or if something is moving across that surface, then it will deflect. And then this picture right here is actually a really good picture because he's showing the throwing, and the yellow path is the ball. So the yellow or the red dude rotates out of frame. The yellow dude ends up catching the ball, kind of like I talked about before. So that's the Coriolis effect. And then back to the video. This is some dudes at MIT that built their own rotating platform. And so they basically are going to toss the ball around. So let's look at it real quick because they show you the other one. These guys are going counterclockwise, right? And this is where the camera is mounted to the ground. So they're throwing the ball. And if you just watch the ball, you can see that it's a straight path. They'll actually trace it here for you in the slow-mo. So they're just straight, right? Now they show you with the camera mounted, it looks like it actually curves. So we're actually on the rotating surface now. You can see that it looks much more curvy. So there it goes, whoop. And then here's the trace again on this next one. So notice they're going counterclockwise, and it appears to curve if you're on that line walking to the right, right? Then this is the viewpoint from the catcher. Looks like the ball is coming at you, and then it just curves away. And then I'm going to fast forward because they're going to flip. I missed it. So now they're switching. Notice now they would be going clockwise, right? And so notice that the ball goes in a different direction now. So if you were the ball, or you were on the path of the ball, notice he's going to throw it at us, and the ball is going to go to the right, which means that if you are the perspective of the ball, it's curving to the left. So let's look at it. There it goes. There it goes again. So notice, and here's what you need to know. If you are rotating, let me see for you guys. So if you're counterclockwise, right? Counterclockwise, which is the northern hemisphere. Anything that's going counterclockwise, when you throw something straight, it is going to curve to the right. Okay, that's the perspective of the path. So if you put your hand in front of you and you start to walk that line, for me, this is curving right, which I know you're looking at me, so that's left, but this is to the right. So if you're counterclockwise, which, sorry, you guys, counterclockwise would be this way, then you are curving to the right, which I just made that perspective look right for you, or correct for you. So it would actually kind of be more like, probably like this. You're throwing it, right? So it is going to curve to the right. Okay, so we'll leave it at that. And then you guys can look at this next video where we explain how this affects wind. So here comes that video here in just a second. Again, we're gonna take this picture. Notice it's the same one. I've just moved north poles here, south poles here, right? And then we've got the equator running along here. And I've done this so that we can kind of see a couple things here, and then we'll flip back to the other one. But basically what I want to do is that. Okay, so remember we talked last time, the air at the equator is rising, right? So we've got rising air there, and then we've got, let me actually switch this for you to blue. Then we'll have sinking air here, right? And then we have air, that cooler air is moving towards the equator here, and then we'll have that air from the equator moving across. So remember, this is our upper level winds. Talked about it before. And then this down at the surface is our surface winds. Now, because we are rotating, so because the North Pole is rotating, this isn't going to be as perfect as we've made it here. And the Coriolis effect is going to come into play. So as this air that is moving in towards the equator, so normally it would be moving into the equator like so, right? And again, this side would be doing the same thing. So it's kind of hard to visualize sometimes on 2 dimensions, but this is kind of what's going on here. Then this is at the surface, what's going on. So I'm going to stop talking about it coming towards us. Here I'm just going to talk about the surface. So if our surface level winds are basically coming in straight towards the equator because air there was rising, right? Then what we're looking at is, for the Coriolis effect, the northern hemisphere, these winds are going to deflect right. So if you are on this path, instead of going straight towards the equator, you would turn and you would curve to the right. This one, instead of going straight to the equator, would turn and curve to the right. In the southern hemisphere, it's the opposite. As these move towards the equator, they turn to the left, right? Now you got to put yourself on the line. If I were on the line walking towards the equator, this would be my left, right? Then this would also curve toward the left, right? So basically all along here, these winds are going to be curving in the north to the right and in the south to the left, right? Now, all of these winds curve too. So really what you end up with as these guys are rotating, you end up with this kind of swirling pattern of winds, which we won't get too much into, but it's basically spiraling. While I've got these up, I do want to talk a quick bit about what's going on here in terms of pressure. So remember, when air leaves the surface, that creates a low pressure, and then up here would be create a higher pressure aloft, or upper level. Then over here, as wind moves that way, it would create, or as air leaves that area, it would create low pressure, and then here would be high pressure coming down at the surface. So if we were looking at this, at these low pressure situations, remember that we could create clouds here, right? For the surface level lows, we get some clouds, and the weather can get kind of nasty, right? And then over here, remember, it would be good weather, because sinking air doesn't like to build up clouds and thunderstorms, right? So remember, our surface pressure lows So surface lows will create cloudy weather or stormy weather, and then our surface high pressures will create clear skies, good weather. Okay, so we're gonna kind of change gears and flip back to this picture. On this picture, we still have the same stuff going on, but let me get my marker up. So again, we had air moving towards the equator, right, and then rising here, and then returning there, right. So you have a low pressure system at the surface at the equator. You'll have a high pressure system here at the surface at the 30 degrees north latitude. And again, laminar versus turbulent, this is just basically crayon drawing. Obviously it happens way differently when you get everything else involved. So but we got low pressure, high pressure. So if we have a high pressure here well, let's look at this real quick. So if we're moving in from here, trying to go straight, we end up curving, remember, to the right. So you end up with this surface winds in this area curving to the right as they approach the equator, right? Now, we have high pressure always moves to low pressure when we're at the surface. So what's going on here is air is moving down. It's pulling air down here as well. We have a high pressure system here. If there's a high pressure system here, that means that air is going to want to move away from that, and there's probably a low pressure system here. So basically we have kind of the same thing going on here, but you'll basically end up with the air going in a different direction. So between these two areas, we have what's called convergence of the air there, and then down at the surface we have divergence. So this is divergent flow. So basically what we have up here, convergent is usually pretty turbulent. You got air mixing together and pulling each other down, and then down here you have divergent that usually sends air out, so it's a little bit more calm. So at high pressure systems you have that sinking air. It diverges at the surface, which typically doesn't allow you to really the point that I'm trying to find here. What I'm trying to do is look at these areas. So if that surface air or surface current or surface wind is moving up towards 60, that means we are trying to go to 60 here, from 30 to 60. We're trying to do that straight line, but again, Coriolis. So now we are going to the right. So now these winds are going right, 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 right. Okay, then up here at the polar regions, you have another low pressure. So air will move this way, right? And then it's going to cycle back that way. So this air is trying to move from the pole down to 60, but it's going to curve to the right. So we got right, right, right. Okay, now, cool thing about this right here is a convection cell, right? Warm air rises, cold air sinks, rising, sinking, right? This is called a Hadley cell. Okay, there's also one right here. Now, because these are kind of the drivers of everything else, the warm air is rising here at the equator. There's a lot of heat that's going in there, so we get a lot of rise. So that right there, these guys will be really, really puffy, right? Then this next cell that goes in the opposite direction is driven by this cell. This cell rises, falls, that draws air down here. So you get a convection cell that's going here. You still have cool air sinking, warmer air rising, all of that's going on, but this cell is a little bit shorter because there's not as much energy in it. So this guy is going to be called a Ferrel cell. I think I spelled that right. Kind of like Will Ferrell. And then there's also a little cell up here. Now this one's going to be even smaller because this one is at the polar region. And there's not a lot of sun input energy there, so the rising isn't near as much. So this guy is called a polar front. They don't call it a cell, I don't know why. But basically you have those guys going everywhere. So down here they're called the same thing in the southern hemisphere. That's your feral cell. This is your polar front, and same on the back side. So what you end up with, you can't see it over here on the left, but what you end up with is the Earth is basically wearing a puffy jacket, right? And that puffy jacket is made out of these cells of wind. And then right in these convergent areas, and then this one would be a divergent area, that is where we create what are called jet streams. So jet streams are basically created in these areas where air is moving away from each other or toward each other, whichever way. But it basically creates that basically an area of low pressure that's pretty intense. And we know from low pressure, when we blow through that tent, that it collapses. Surrounding air wants to move into it. So that ends up getting these really fast air currents aloft that jets actually use to travel from northeast. So anyway, the jet streams in the northern hemisphere will run west to east, and then in the southern hemisphere, same thing, west to east. But anyway, what we want to look at is these surface currents here. And in order to do that, I probably need to erase some stuff and come back. So let me pause. So we're back, and let me put my brush back on. So as we were looking at these winds, remember these guys were coming in and turning right, in, right, in, right, right. Then these were doing the same thing but going left, right. Then at these they were going here, 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 and then these were doing the same thing as down by the equator, right. Then in this one, these would be turning left. Wrap my head around that. Left, left, left. And then these would be doing, sorry. So northern hemisphere, you have near the poles, you have surface wind, or I'm sorry, the equator, you have surface winds moving in and turning right. So if we look at the cardinal directions, north, east, south, west, right? Then when we look at these winds, these winds are coming out of the northeast. So these are called northeast trade winds. Call them trade winds because early shipping days, they used these guys to travel basically from Europe over to the Americas. You could basically get in these northeast trade winds and they would bring you down to the southeast, right? Now, up in the next layer in the temperate zones or in the subtropics, these winds are coming out of the southwest, but for some reason they just call them westerlies. I guess the further you get north in this, the more westerly they are, maybe. But basically we're just going to call these westerlies. And then these guys up here end up being easterlies. And then if we look, same thing happens here, southwest trades, and then this would be easterlies, and then these guys would be westerlies. So those are the winds or wind patterns on the Earth's surface. So these are all surface level winds. And again, they're driven by the heating of the Earth at the equator, which causes low pressure. Then you get those convection currents, which down cycles the next cell. So you get Hadley cells, feral cells, polar fronts. But at the surface, you have those surface level winds moving toward those low pressure zones. And then because of Coriolis, they're going to turn right in the northern hemisphere, left in the southern hemisphere. If you have all that, you should be good. Hopefully this wasn't too terribly confusing. Sorry, I know you guys thought you were done, but I wanted to kind of bring this back up and just make it as straightforward as I can. So this is maybe a better picture. The only thing missing on this picture is this is the equator. This is 30 degrees north. This is 60 degrees north, 30 south, 60 degrees south. So notice that on this, they call this one a polar cell. Some places call it a polar front. I was wondering, in fact, on the other video why it's called a polar front and not a polar cell. This one calls a polar cell. So Hadley cell, Ferrel cell, polar cell. Everything here kind of looks good. They've said this is warm air rising here, then cold air sinking. Cold air sinking here, warmer air rising here. Now, when we're talking about this warmer air, it's warmer compared to. So, don't put a whole lot on that. But one of the things that I wanted to make sure we got is really there's two things. First of all, these winds, they got their name from sailing. So I was wondering why they're called westerlies when really they're coming out of the south. They're northwest, and then up here they're coming out of the southwest. The primary reason is this: if you are in Spain, right, and Spain's right here, let's say, which that's an awful Spain, but whatever, you get the idea. If you're in Spain, if you get in your sailing vessel and you want to sail to the Americas, you basically catch these westerlies, and they will take you down to essentially the coast of Florida. That's pretty bad, Florida too, but take you down to the coast of Florida, right? Then if you want to return home, you would sail up the coast, and then you would hit these westerlies, and they would send you back home. So basically, these guys, these were called trade winds because you could use these to trade with the New World, right? And then you would use these westerlies to bring you back home. So it basically set up this nice, easy trade route between Europe and North America. Now, there's an area here on this map. It's not listed on my map. I had it. It's called the doldrums. And that doldrums area is an area. This all shifts, by the way, because we have the tilt of the Earth, right? The equator in the summertime really is up here in terms of heating, right? And then in the wintertime, or in the summertime in the southern hemisphere, it's down here. But basically these guys would travel, and when they hit this zone, there's not a lot of wind. It's a lot of lift, and really the wind is converging and then just lifting. So there's not any wind that can push their sails. So this area was called the doldrums, which I had written on the other map, but it's the doldrums. Let me get my pen. It'd be way easier to write. So it would be the doldrums, right? And that's an area where there's very little wind. And the reason they called it, or you hear about sailors talking about being in the doldrums for months. And it was usually when they're trying to get to these southern latitudes, they basically have to go down. And once they lose wind, they might get stuck here for days before they pick up these southern hemisphere winds. And when they do finally pick these up, they can start to travel this way again, right? So excuse me. So basically that's just a bunch of kind of trivia stuff. What you really need to know, though, is that those cells, those Hadley cells, and I alluded to this, I just wanted to clear it up. I said they're puffy jackets. And so this is happening all across this area, right? So that ferrule cell extends all the way through here, and then that polar cell is all the way through here. This Hadley cell goes all the way through here. This ferrule cell goes all the way through here. It actually goes more down through here. I kind of jacked that up. And then this guy goes up through here. So it looks like the Earth is wearing one of those puffy jackets with the, Michelin Man layers, right? Obviously, it's not, laminar turbulent. It's not exactly along those boundaries. But in between these boundaries is where our jets typically lie. So if you've ever watched the news, you can see this jet sometimes will dip way down and come back up. So these things aren't perfect. It's not like this beautiful looking symmetrical thing. It's got a bunch of mess going on it. And then the other thing I alluded to is that at the surface we have this wind, and then we have rising, and all of that is turning right. So in this Hadley cell, you have this spiraling convection cell that's moving along. So it's not as simple as just this this convection cell here of rising and falling, right? So be careful with some of this. Don't think that, oh, this is exactly how it is. There's a lot of things at play. But there is some interesting stuff too that when you look at hurricane season, if you've ever watched hurricane season, the coast of Africa is over here, and you'll always see the hurricanes will travel right through here till they get to Florida or the Caribbean or whatever, and then sometimes they might turn north, and that's usually because that jet sometimes will dip down, and that jet will steer them back this way. Once they start getting shear, then it starts moving them off their path, right? And so as you'll actually see as summer and in early summer, they typically are kind of coming straight across that path, and then as we start navigating back towards fall, it starts becoming where they dip a little bit further south, because the equator is, from the sun's direct energy perspective, is moving south. So you'll actually see those hurricanes track a little bit more south, and that's when they tend to get in the Gulf a little bit more frequently, especially like this year. We had tons that ended up in the Gulf. So usually your earlier hurricanes typically take kind of that more northern track. It's not always like that, but typically it's more that northern track and then curve off. And then as we get later in the hurricane season, they can kind of dive a little bit more south. But don't quote me on that. It's just kind of a general thing. Obviously, like I said, this isn't a perfect world. But those are kind of some things that I just wanted to clarify before we moved on. Most important thing is this, and I think I've said it in every clip of this video, but the most important thing is that, let me just write it right here. The sun drives all of this. So sun, remember, heats up the air near the poles. That air rises, creates low pressure at the surface, high pressure up here. This would be a low pressure here, which would create a high pressure down here, right? So notice these are surface highs, surface lows. So highs, 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 lows, 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 right? And then this Hadley cell is what drives the rest of it. Because this cell is going from the sun directly striking here, that's going to drive this conveyor belt-like system. This does that, drags this one down into the mix, then that one kicks that one up into the mix. Because we don't have the same heating going on here to drive that, we drive it here, and then that creates everything else on a conveyor belt-like system. So the sun drives that, then that causes wind at the surface to move in towards the equator. Okay, so those surface level winds are moving towards the equator. So you've got sun. Then second is wind toward equator. And that wind turns because of the Coriolis effect. So remember, the sun basically is going to drive this. It heats up air at the surface. That air rises at the equator. Air then at the surface near the equator moves toward the equator, and then Coriolis causes that air to turn. In the northern hemisphere, we turn right. So if you put yourself on any of these lines and walk the line, I am turning to my right. And then on this side, I am turning to my right. And I'm turning to my right. So put yourself on the line, walk the line towards the end of the arrow, and see which way you're turning if you need to. But you're always turning right in the northern hemisphere. And then in the southern hemisphere, you are turning left. So the northern hemisphere, when viewed from above the South Pole, is counterclockwise, and then in the southern hemisphere, it's clockwise. So I think that covers everything. I know it's like kind of another one of those ones that's a little bit all over the place, but Hadley cells, Ferrel cells, polar cells, driven by the sun, turned by Coriolis, and then that's going to cause surface winds to deflect from their intended path, turning right in the northern hemisphere, left in the southern hemisphere. And then that's going to set up what we're going to talk about next, which is going to be currents, ocean currents. So if we know this, we should be good. We should be set up. There's just going to be a quiz about it, so look at it, do it. There's also a video that I'm going to post on there. It's Destin and what's his name? Can't think of it right now. Derek. So Destin and Derek are doing another video about the Coriolis effect because some people say that toilets in the northern hemisphere go clockwise or counterclockwise, whatever it is. They turn right, so I guess clockwise. And then in the southern hemisphere, they go counterclockwise. That is partially true. Some people say that has the Coriolis effect won't affect a toilet like that, so it's not a big enough surface to affect. So it's not true, which is also partially true. So Derek and Destin decided to make a big video where they do an experiment. One of them in the northern hemisphere, one of them in the southern hemisphere, where they test on a larger body of water to see if you do pull a plug, if you have that swirl effect. So it's a pretty interesting video. I'm going to post it in there. You actually have to open it. I'll actually show it to you real quick in terms of how to work it because it's weird. But that video, when you post it in, it's going to... it's the Smarter Everyday link. When we pull that guy up, there it goes. You'll come to a screen that has both of these. You'll want to actually click both of them basically at the same time. And when you do that, it syncs both of those videos, and then they basically, at first it's weird, so get by that first 30 seconds because they introduce it and they're both talking at the same time. But then it goes where they're basically, one of them is shooting the video in the southern hemisphere, one's shooting it in the northern hemisphere, and so they, in the way that they kind of have the playful videos, they then sync off of each video. So one will talk, and then he'll talk about the northern hemisphere and what's happening, and then he'll switch over, and the other one will talk about the southern hemisphere. So it's fun to watch in that dual thing. So I would suggest doing it that way. And then it just kind of fleshes out the Coriolis effect. So I'm gonna post a link to this site here, and then when you get in there, click both at the same time if you want to watch it. It's kind of cool. Again, I'm a nerd, so apologize if you don't like it as much. If you don't, then don't watch it. So anyway, take that quiz. Next time we'll talk about currents. Until then, enjoy.